All right, good afternoon. Last week, huh? Almost. Oh, second to last. Last week of normal classes, right? Okay, so that means we are wrapping up today in terms of lecture material. Had a couple of you ask me here and there about what's on the final exam. My plan right now is for it to be about halfway stuff that we've been covering since the last exam, and the other half kind of comprehensive with previous topics. But as you'll see, even today, we're going back and visiting stuff we've talked about before, the first couple sections. So it's all going to be a little bit cumulative. It's all going to be equilibrium chemistry. So I will specifically focus on stuff from this third homework for about half of the exam. Okay, and I'll probably touch back on a couple concepts from the previous exams. I'll remind you again at the end of the lecture, but the course evaluations are out, so I'd really appreciate your feedback there. Happy for you to be completely honest. It is anonymous, so you can put whatever you like, and I'm going to read it. And I appreciate especially constructive feedback, but even if you just want to vent to me because something frustrating happened, I do actually want to know that so I can know to avoid that, right? Okay, so with that, I want to touch on a few things for the carbonate system. Wanted to clarify a couple pieces for you, tie in the solubility aspects, and I think we'll have some extra time if you wanted a little bit of coaching with MATLAB and okay, where do we start with this thing? Talked with a couple of you earlier today even, and I felt like that was perhaps very helpful. So I'm going to probably give that sort of a session as well, kind of like we did with Excel that time. So with that, I'm going to get going so we can have a little time for that. So looking back at the closed system, we talked about closed and open carbonate systems last time. We said that they were essentially diprotic acids is one way to look at it. And a very generic plot would look like this if we're going to plot the log concentration versus pH. Of course, we could plot it as log, we'll just do that. Log concentration versus C on the y-axis there. We could plot C versus pH. The graph's going to look a bit different. It's going to be a lot sharper. We're not going to see as much. So typically we plot log-log because these concentrations fall off pretty quick. So we've seen a lot of graphs like that. Usually we were focusing on a monoprotic, so there's just one deprotonation, but this is not too much different, right? And if we want to get lines for each one of these, or kind of y equals mx plus b sort of a deal, a function for each one of these, one thing we can do is recognize that while we have for a closed system a specific total concentration, carbon total here, or carbonate, whatever you want to call it, and we could define each of these based on that total. The way to do that would be, first of all, to say, well, the carbonate itself, the carbonic acid, H2CO3, that's going to be alpha 0 times Ct. Then, of course, the next one, bicarbonate, would be alpha 1 times Ct. And carbonate would be alpha 2 times Ct. So we have all of those equations, and if we want to, we could put that, just go ahead and take the log of this equation and get it as log concentration equals, and you can do the little log trick and add them when you're multiplying, do log A plus log Ct. It's the same thing as taking the log of both times each other. So that equation, log of alpha times C, is the same as log of alpha plus log of C, right? It's just a little algebra thing. So you can put it that way. You can also calculate it and then later take the log. That's probably what I'm going to do in MATLAB just to keep my head on straight. So whatever you like to do, but just notice that we can set up something that in a way looks like y equals mx plus b, where x is our H plus that we're going to convert to pH, and the y is whichever line that we're going to plot, right? I'm just going to say carbonate of some sort. Okay, makes sense? So for the closed system, we use the alpha fractions and the C total. We need to know something about C total so that we know how much is there that to, at some places, it's basically all in one form or the other. So that's kind of our limit. So we need to know CT for a closed system. Now the alpha fractions, we might be thinking, okay, where do these come from? I'm going to remind you today of how we derive them into a useful form, into the H+ form. We've gone over this before, especially with the monoprotic acid system, and this is stuff you can look up, but I wanted to just take you stepwise through it, kind of remind you, refresh your memory of where this is all coming from. I glossed over it last time, so I was going to give it a little more clarity here. So if we wanted to calculate these, well, we have alpha 0, alpha 1, and alpha 2. Of course, the definition of one of the alphas is the fraction that is that species, right? Alpha 0 is the fraction that is, so alpha 0 means it's lost 0 protons, so that would be H2CO3, right? And the simplest way to write that would be H2CO3 divided by C total. Another simple way to write that would be HCO3 divided by each of the carbonates added together, right? H2CO3, HCO3 minus, and CO3 minus, right? All tracking with that? It's just very essential, straightforward mass balance here. Now what we can do is we can write that for each of them. Alpha 0, alpha 1, and alpha 2. And all we're changing really is which one's on top. Okay? So once we do that and we start simplifying, the first thing we can take a look at is what happens if we divide the top and the bottom by whatever's on top. So we get it to a clean 1 on top, right? And we've actually done this a lot. It's often been in the background, and that'll start looking like 1 over 1 plus blah, 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 blah. Okay? Once we get there, we can do some further substitution. So the next slide, I'm going to kind of remind you of that typical process here. And our target here, of course, is to convert each of these alpha fractions into H+ and K. That way, we know the Ks. It's going to be more than one K, right? K1, K2. And the H+ is going to vary, right? So that's going to be the X. So when we plot y equals 2x, we know that we selected 14x values and we're calculating 2x every time. Okay? So when we set up our equation, we want to get alpha in terms of x, or rather H+, and some constants. So that's what we're going to, and if we stopped and looked at it right now, well, we don't know what each of these are, right? We have to figure them out. So that's why we're going to do the algebra to simplify these into H+ and K, like into a form of those. So we've done this, like I said, with the monoprotic. I even have, I think this section, I went ahead and put it on your formula sheet. I think even last time, maybe even the first exam, I don't remember. So you've seen this, but what's happening is we're taking from one of the alpha fractions. We're going to start with the monoprotic just to show you the way we're doing it. Alpha 0, that's the fraction that is HA. So it's HA divided by the total. We can divide that, well, we can also say A1, alpha 1 is A minus divided by the total. Now, we also know, of course, these guys, alpha 0 plus alpha 1 is equal to 1 for monoprotic. We could say plus alpha 2 if it's a diprotic, and so on. So we know all that stuff. Now, once we have this form, we divided the top and the bottom by HA. So it's 1 over 1 plus A minus divided by HA. Here's where we do a substitution. And we can do this with a diprotic also. What we substitute is, well, if we have some ratio of A minus to HA, we can always get the equilibrium equation Our equilibrium equation, remember, is K is equal to the products over the reactants. We can always get this in the form of a ratio. We can rearrange it to get it as a ratio like the thing that's showing up down here. So we can always do a substitution from our equilibrium reaction into that. Now, remember, I'm not asking you to be able to derive every single piece of this. Maybe for the monoproduct. Diproduct, it's the same deal. It's just a little much, right? But I've already told you I'm giving you this little thing on the formula sheet. So even if I did ask you to derive it, you just have to remember, hey, there it is, and fill in the pieces. So I'm just reminding you where we're getting all these pieces and how it kind of fits together. So we take from these alpha fractions, we send the substitution in. And what we have then is the K and the H plus. Right? These guys are really what we want to focus on in terms of those are the useful pieces because those are the knowns, especially when we're plotting it against pH. We know the pH because we selected, okay, we're going to plot this. Now, of course, we're going to have to flip it, and reverse it to substitute in there, but it's the same deal. Yeah.
Does the same conventions apply for diprotic acids? So like A naught plus A1 plus A2 is equal to 1?
Yes. Yeah. So the alpha fractions are really always just saying the fraction of the total. So if you have more species that include the fraction of the total, you will have the A2 there, or the alpha 2. And the same process that I'm doing right now, we can do with the diprotic and triprotic also. Okay, so once we've sent the substitution through, that's when we end up with alpha 0 as a function of any of the alphas as a function of Ka and H plus. Okay, so it's just algebra to get it to the point where we have our equation in the form of H plus and K. Now, you'll notice here you can also, if you wanted to rearrange the simplification, have it in a slightly different format, you could put alpha 0 as H plus over H plus plus Ka, right? If that happens to be more convenient, if you like it better that way, whatever, that's fine. So that's where, this is the procedure that we're getting the formula for the lines that we're going to plot. Okay, this is all that background to derive the alpha fraction that goes into Ct times alpha 0, 1, or 2. All right. If we do this with a diprotic system, so, well, we'll start with monoproducts. We just showed ourselves we can get to this 1 over 1 plus Ka over H plus for alpha 0 in a monoprotic system. We can do the same thing for a diprotic, and what we have is essentially two substitutions that we need to make because we had what, for a diprotic, we'll call it HB divided by HB plus B minus, H2B by HB minus and B2 minus. Okay, this would just be the same deal as the carbonate system, where B2 minus would be CO3 2 minus, right? So we can see that the same deal applies, and all we have to do is do two substitutions, which brings in our K2 in addition to the K1. So I don't want to, spend too much time on the derivation, but it's the same exact thing. Okay, yeah.
Would it be important to know how the third term is derived?
The B2 minus here?
Yeah.
Well, I can go ahead and write that up. So all we have to do really is to think about the B2 minus. That's going to come from the equilibrium equation. K2 is products over the reactants for that equation, right? For that equilibrium. So there should be an H plus and an HB minus, and a B2 minus coming as the products of the equilibrium reaction with HB minus. right? So the other way to write that is to say that HB minus is in equilibrium with H plus and B2 minus, right? So that's our second equilibrium reaction. And so that's going to come, so when we substitute for B2 minus here, we need to substitute that in there. Now, it's a little, there's another step here. You see the K1 involved. That's because the substitution we did for HB minus shows up right here, and we just multiply that. I'll pause and show you. So I'm going to finish rearranging this. So let's imagine for a moment I did 1 over 1 plus HB minus over HB plus B2 minus over HB. That was the step before, brackets on everything, of course. I'm trying to substitute in for this, right? And so here's where the K1 over H plus goes to this term. And then what do we do for the next term? Well, we have it as a function of, we're going to find that we can get HB minus, we can get that same substitution here, right? So we can write B2 minus as a function of HB minus. So I'm gonna do that, try to explain that. So if we do K2 divided by H plus, on the right side we're going to have B2 minus over HB minus. Now just a minute ago we did a substitution for HB minus, right? We had just done that in this situation to say that, well, HB minus over HB was that K1 over H plus. So when we're trying to deal with then a situation where we have B2 minus, and we don't know what B2 minus is, over HB, well, instead of writing it that way, we can take it and say that B2 minus over HB should be K2 over H plus times K1 over H plus. Because if we take, I'm going to use a different color for a moment. If we take this guy and multiply it by, where was I? This guy, we end up getting the thing that remains would be HB minus divided, oh, excuse me, not, that would be B2 minus divided by HB, which is what we're trying to substitute. Yeah.
Why does the HB on the top have a negative charge in the one bottom?
I meant to give that a negative, I'm sorry. That should be H2B every time I wrote it down there. Very good catch.
So would that just be one then? Oh, H2B.
Yeah. My bad there. So it does all make sense, and maybe even my next slide might even show that a little clearer. The point is that we can get it in the form of the K's and H's by sequentially doing that substitution. Okay, So don't stress too hard if you didn't follow every last piece of this. Just follow that we can use the equilibrium reactions to substitute appropriately and get these alpha fractions as a function of K1, 2, and even 3 if we're doing triprotic, and H+. And you can see it's sequential like this. So if we could maybe imagine a 4-proton acid, and we could keep going with it, right? Okay. We're all right on that? Okay, so here's the general form then. For HA, for H2B, and H3C. Assuming you remember to keep the 2 there, which, you know, apparently I had difficulty with. You can then write alpha 1 is actually equal to alpha 0 times Ka over H+. Or you could write alpha 1, so that's true for the first deprotonation regardless. Or you could even go to alpha 2 and put that in terms of alpha 1. So that I wasn't, that's kind of what I was showing just a moment ago. We can actually put one of the alphas as a function of the previous one. So alpha 1 equals alpha 0 times Ka over H+. That comes from those substitutions we were just doing. And if you do the algebra out, you'll see, yeah, it makes sense. That works. So that's just from those substitutions. Alpha 1 is alpha 0 times K1 over H+. Alpha 2 is alpha 1 times K2 over H+. And we could continue and do more from there. Okay, so that's another way to express it relatively cleanly as that function. You don't have to look at it that way. You could just derive the full thing or use the full derivation already. But if you do the derivation process, you'll see that that's what we were just pointing at a moment ago. Okay, so for the open systems then, well, I'll back up one step. For the closed system, when we want to go graph these, what we're looking for is the 3 equations, right? Ct times alpha 0, Ct times alpha 1, and Ct times alpha 2. So we simply need equations for each of the alphas. And we also need Ct, which is usually given, and on the MATLAB assignment it is given, right? So you just need equations for the alphas as a function of H+ and the K values. You have that here for alpha 0. That's 1 plus, so 1 over 1 plus K1 over H+, plus K1 times K2 over H+ squared. Now, to go from there to get to alpha 1, you can use this equation. You take that same alpha 0, multiply it by Ka over H+. Right? For alpha 2, you can take the one you just calculated for alpha 1 and multiply that by K2 over H+. And there you have it. So you'll see that starting equation right here, it's a little bit of a mess, I'm sorry. Starting with this guy, maybe I'll clean that up for you so that it's not so messy when you look at it. When you look at this guy, you can just see how if you multiply this by a K value divided by H+, you'll end up with a K here. This will turn into H+, and you'll get rid of one of these and one of these. And when you do alpha 2, it's going to shift it over, so then it's 1 over H+ here, or no, it's going to be H+ squared, K1 times H+, and no H+ at all down there for the alpha 2. And on the top, it'll be K1 times K2. So you'll see it feels like it's just a nice little sequential change. And if you stop and think about it, it kind of makes some sense that you can feel the graph should shift somewhere based on the pH, based on what the denominator looks like in terms of how much it depends on the H+. So even if you can't imagine exactly what these lines look like, you can get a feel for, oh yeah, we're definitely changing something about how the denominator depends on pH, right? That much is clear. So you'll see that as you write all those out, that's a good spot. So when you go to make a plot for your system, a good idea would be to go ahead and list out, make a table. Okay, here's my x values, here's my y for the first one, make some values, y2 for the next set of values, y3 for the next, and just have yourself be ready to say, okay, what's my equation to calculate y1? Okay, and for each of these, you're going to calculate H2CO3, HCO3 minus, and CO3 2 minus, and so on, right? So hopefully that's a good way to be thinking about how am I approaching this problem, okay? How am I going to set up a graph? Now for the open system, it's a little different. It turns out it's a little simpler in a way. Our starting point is the fact that our CO2 is in equilibrium with the atmosphere. So for the open system, we have basically an infinite amount of CO2 that can come into solution because we've got lots of atmosphere. It's not fully concentrated, so there's going to be some equilibrium that we find there in terms of how much goes through, but that's going to be defined by the partial pressure given. I think I gave you guys 500 ppm in the assignment, and the Henry's law constant. So maybe we're talking about in a little greenhouse where people added a little CO2 or something. Okay, so the H2CO3 then, that's held constant in solution. So no matter the pH, the water is just going to hold that much carbonate in terms of carbonic acid, that much dissolved CO2. So that line's easy. Once you calculate that, it's just, that's your line. It's a flat line, just a constant throughout all pHs. And you see there's no pH dependency here. Now, next up, bicarbonate. Here we have to go and think about, well, how do we use the alpha fractions and all that? And in this case, rather than use the alpha fraction and associate it with CT, well, CT changes. And so since CT is not constant, we have to use a different approach. It's very similar, but it is a little different. So we don't use, let's say, HCO3 minus equals alpha 1 times CT because CT changes, right? So we can't use the same exact formula that we did for the closed system. Instead, what we could say is, well, we do know how much H2CO3 there is, and we do have a relationship between bicarbonate, HCO3 minus, and H2CO3. That's our first equilibrium reaction. So we could just use that. So we'll use this HCO3 minus based on our equilibrium equation. All we have to do is rearrange it a little bit to say K1, so HCO3 minus is equal to K1 times H2CO3 divided by H plus. Okay, so that's literally just taking, it was products over reactants. We multiplied everything by the H2CO3 and divided everything by the H plus, so we isolated HCO3 minus. And there we have it. We have a function of pH. We have one known here, and because the carbonic acid is also a constant, we have another constant there. So now we have a function, we have it as a function of pH and knowns. Okay, so that's really all you need to do. You could also rewrite it if you wanted to as K1 times the Henry's law constant times the partial pressure. That'd be fine too. Doesn't really change. Then for CO3 2 minus, it's the same deal. We just have to do the substitution twice over. right? So we substituted once to get to HCO3 minus, and we could either take that and substitute in with our second equilibrium reaction. It's probably the best way to look at it. And now that we know at a given pH, we had a way to find the bicarbonate. Now we can find the carbonate. Okay, so if the three lines that we're going to plot in the closed system were the alpha fraction plots, in the open system, it's similar, except that we are not basing it on CT, we're using it just these equilibrium reactions. So here would be 1, 2, and 3 for the open system. Of course, you also, in this case, we need to plot CT, it's changing, which is just going to be the sum of each of those, right? At a given pH, we're looking at 1 plus 2 plus 3, right? It's just the total. Okay, so when I lay it all out that way, hopefully that assignment becomes a little simpler, more straightforward. Okay, I kind of did all the chemistry for you here to just show you that part. So it's mostly a MATLAB exercise, but I think and hope it'll connect you to the chemistry tangibly as you work through it. Does that make sense? Okay. All right, so I'm sure we will have some time, and I can tinker with you with MATLAB here if you'd like. Maybe take a look at some of the homework, the general homework problems as well, if there's any questions there. But for the moment, I'm going to pause that and wrap up just a little more discussion about alkalinity, mention hardness, and we'll basically be done with the lecture side of today. All right, so alkalinity. In the carbonate system, you know, we talked about it a couple times by now. The way we define alkalinity is very close to the way we were defining that acid neutralization capacity that was so important for titrations, right? In fact, it is very, very much the same as that concept. Of course, we can have some other weak acid that would contribute buffering capacity, but if we just have the carbonate in the system, the carbonate itself will act as a buffer. So there's really two things to keep in mind. And I know we didn't do diprotic systems with buffering and all that. Don't worry too much about that. It's almost all the same. Here's a couple little key facts that we can latch on to and understand what's going to happen with the carbonate system in terms of titrations. So with carbonate, we often titrate with an acid. So we often might start with a basic condition and add acid until we've driven all of it to dissolved CO2. Because alkalinity is acid neutralization capacity, right? That's one way to understand it. Of course, we could add a base and see how long it takes before we get to everything to CO3 2 minus. But oftentimes we look at it in terms of adding an acid to it and seeing what happens. So if we start with some solution and we add acid until we reach pH 8.3, we will have, we'll have essentially converted all of our carbonate, CO3 2 minus, to bicarbonate. And if we look at the one of these graphs, maybe I have one earlier, we can see that pH 8.3 is right there. I didn't draw that very well. Is right there, kind of at the midpoint where we definitely have the most bicarbonate. In fact, it's probably crossing exactly in that in-between line. Okay, and so that, once we reach there, that is the point where we have the most bicarbonate. There's almost no carbonate left. We've converted almost all of it, effectively all of it, meaning it's like 0.000001 of it. If we have this much carbonate, total carbonate, we only have a tiny, tiny bit of carbonate remaining, right? So the point is that when we pushed that graph to pH 8.3 by adding acid, we've gotten rid of basically any meaningful amount of carbonate, and really also any large amount of OH minus. So pH 8.3, there's going to be some OH minus, but it's pretty close to pH 7. At pH 7, we have 10 to the minus 7, which is a very small number when we're talking about how much alkalinity we have. pH 8.3, okay, maybe the OH concentration is like 10 to the minus 5, but that's still a very low number compared to other things that are alkaline. When we're talking about alkalinity in terms of like milligrams per liter of stuff, that's still negligible. So both of those, so we convert the majority of the OH minus to H2O, and the majority of CO3 minus to HCO3 minus. So basically we're getting rid of the remaining capability of those species to buffer the system against acid. That's the point. So when we reach there, that is our first endpoint. Now the second endpoint would be this one actually falls within a range. So the first one you could see that it's kind of precise. It's right between the where those two species, the carbonate and the carbonic acid, meet. Right is where we have the peak bicarbonate. Now the next endpoint, this is essentially our HA equivalence point. It's how we previously referred to it. There's actually a bit of a range because it depends on how much alkalinity we had in the first place and how much total carbonic acid we have. So but it'll typically be around pH 5, maybe just under, maybe a tiny bit over. And we can see the little table here shows a few endpoints that we could find, 4.9, 4.6, 4.3, depending on how much total alkalinity we have in the solution. So basically, that endpoint happens when we've converted all of our bicarbonate to carbonic acid. And by all of it, I mean, any substantial amount. So those are the two endpoints, and we can then understand what happens when we titrate a solution going to those endpoints. So we can label these as V1 and V2, where that's the quantity. The V is the quantity of acid required to push the solution to that endpoint. So we're going to start in a basic condition. We've seen these plots usually flipped. So we're adding base and climbing the pH ladder. This time we're going to start at a high pH and climb down by adding acid. Okay? So we start at a basic condition, having added exactly 0 strong acid. So we're going to plot this as a function of strong acid added here. We could also flip this if we do net strong base and do a negative net strong base as the acid. We could do that too, but okay. So if we go then and start adding acid, we can add it until we reach pH 8.3, and we'll see that we're finding that equivalence point here. That would be our V1. And if we had a concentration here of 1 times 10 to the minus third total carbonate, this was added as Na2CO3, so sodium bicarbonate. Well, we just added exactly 1 times 10 to the minus third moles per liter of strong acid. So that's exactly enough to get us to that first end point. And in fact, that probably we could relate that to the equivalence points we talked about in the past, but we're going to have 2 of them instead of 1 of them for our diprotic system. Okay, so that's our first endpoint, and we'll call that V1. When we get to V2, if we continue adding acid, this one we can see crosses somewhere, it should be somewhere near pH 5 or maybe a little below, right? Here, once we added enough to get to V2, and this is exactly 2 times 10 to the minus third moles per liter, now we've used up all of the alkalinity. Okay, So this is, V2 gives us the total alkalinity. That is the definition of that second endpoint. And what you might recognize is we started with exactly 1 times 10 to the minus third moles per liter of this sodium carbonate. And it took 2 times 10 to the minus third moles per liter of acid to get there. You could think about that because in the terms of that proton balance. For every 1 carbonate, if we're moving it from carbonate to carbonic acid, we consume 2 protons. So for every 1 mole of the CO3 minus, we need 2 moles of acid to completely wipe it away, right? Because when we add Na2CO3 to water, that's going to give us 2 sodiums and 1 CO3 minus. Okay, and our proton balance tells us to get from CO3 minus to H2CO3, we need 2 protons. Okay, so it's pretty straightforward here that V2 is going to give us the total alkalinity for a system. Now, sometimes we might also be interested in, well, how much of our alkalinity was associated with what we call the bicarbonate, H2CO3, excuse me, H3OC minus, bicarbonate. And we could simply subtract V1 from V2 and get that. And that would be our bicarbonate alkalinity. In this case, that would be exactly 1 times 10 to the minus third moles per liter. Now, maybe you have some unknown water and you're not sure how much of it is bicarbonate versus carbonate. Maybe you start at pH 9, so most of it's bicarbonate. That's when this V2 versus V1 might be a little more interesting. And remember, the V1 occurs when we get to that pH 8.3. It's always going to happen there, right at that equilibrium. And that gives us a nice, convenient way to say, okay, well, everything above that was not the bicarbonate stuff. Everything below that, to get to our total endpoint at V2, that's our bicarbonate stuff. Regardless, if we add enough acid to get to that second endpoint, then we've gotten rid of all of our alkalinity. And remember, we can define this based on the curves, right? We defined those inflection points. That's when we recognize that we've used up we've reached that endpoint. We've reached that equivalence point type of situation. So even if we know that 8.3 happens pretty exactly, but this one might get shifted a little bit, but we could still find that inflection point and find it. Now, if we don't have much carbonate at all of this kind of gets a little flattened, and it's a little more of like a straight line with a tiny bit of squiggle. So the whole method falls apart a little if we just have almost no CO2 dissolved in the water. So if we had water that was too pure and not mixing with the atmosphere, it'd be kind of hard to do any of this analysis. It would still technically hold true, it'd just be hard to find any of it if there's just a tiny amount. But small details, and normally we can manage. There are some common indicator chemicals that help us see the color changes with these types of things. So if you've ever done, you probably will see this in the lab class, I would bet. It's an alkalinity test, and you would find the color change and all that. Give you a measure of the amount here. Okay, does that make some sense? See how that's working? So this should tie into at least 1 or 2 of your homework problems, I think, is that concept of, hey, we can titrate this with an acid and figure out, well, how much acid we have to add is that acid neutralization capacity, right? It's pretty straightforward. And that's, again, that also comes from when we talked about the net strong base stuff, where we took all the cations, the electroneutrality balance, where we had the non-pH related stuff, all the strong base cations and strong acid anions on the left, and what was on the right was the carbonate species and any other buffer, any other weak acid. So if we just have a carbonate system, that's the strong bases and cations on the left, and the carbonate system on the right. And that's our alkalinity. Okay. Okay, so a quick example here. We can calculate the alkalinity of carbonate and carbonate species from some titration data. So let's imagine we take a 100 ml sample with an initial pH of 7.2, and it required 8.4 milliliters of 0.0205 normal HCl, that's moles per liter of HCl, to reach the total alkalinity endpoint V2. So it took that much acid, compute the total alkalinity, and determine the equilibrium concentrations of the carbonate species. Okay, try to get the first part of that, and we'll let the book do the speciation. I think you guys can probably do that. So let's give that 4 or 5 minutes to work on that. Okay, so hopefully you were thinking to yourself, well, we've got some amount of acid, some concentration here. Well, we can figure out how many moles of this acid we added, right? And we added it to 100 milliliters of solutions. We'll have to account for that. Figure out, okay, really how many moles of acid did we add per liter of solution? Okay, that's something along those lines, hopefully the direction you're heading. So that's my first thought, right? So we can take 8.4 milliliters. You can divide that by 1,000 for 1,000 milliliters in 1 liter. I went ahead and just kind of did that. I just pulled up Excel real quick to do that. Or you could say 0.00084 liters times 0.0205 moles per liter. The normal, if you recall, the N here, that means 1 unit of something, usually H plus, per liter. 1 mole of that per liter. So it's like 1 normal would be 1 moles per liter. Since it's H plus, it's exactly 1 to 1. If we had something like sulfuric acid, you get 2. You often write it as normal because we're referring to 1 proton. That's the way to normalize it because you need half the amount of sulfuric acid with 2 protons coming off every time. Anyway, don't worry about that. This is molar, effectively. Okay, so anyway, we get 1.72 times 10 to the minus 4th moles of acid that we added, but we added it to 100 milliliters or 0.1 liters. So I went ahead and took that moles, divided it by the 0.1 liters. So effectively per liter, we're adding 1.72 times 10 to the minus 3rd moles. Now, I think the book will show or tell us, and I didn't really get into this too much with you, but the best way to express that would be to say equivalence. This number of equivalents of acid per liter. So that way when we express our alkalinity, it's equivalents per liter. So equivalent amount of acid that it can neutralize, that's the acid neutralization capacity per liter. So we'll double check that, but I think that should be our total alkalinity. And then when it asks us to determine the equilibrium concentrations of the carbonate species, I guess we do that at pH 7.2, or maybe they were thinking go ahead and recalculate the acidity and then calculate them. Either way, that's just going to be the equilibrium reactions, how much carbonate, how much bicarbonate, how much carbonic acid at pH 7.2. We would also need to know the total, the C total, which we can find based on the alkalinity. So there's a few more pieces that we'll do. I'm just going to let the book show us because I don't want to spend a ton of time on it. Yeah.
So would we use the pH to find the H plus concentration and then plug them into the alpha fractions?
Exactly.
The K1.
Exactly. Yeah, and we need the CT value, but we get that from the total alkalinity calculation. I think is the way they're going to show that. Okay, so yeah, they do the same part I just did, and they said, okay, that is 1.722. They're putting it in milliequivalents per liter. That's actually probably the most common way to write it. I was talking about equivalents, but milliequivalents kind of puts us close to like milligrams per liter type of a deal, even though it's molar-ish. Okay, so anyway, we can convert that. Again, I didn't really talk about this, but a common convention, if we wanted to express it differently, we can express it in a unit that's milligrams per liter as CaCO3. Don't worry too much about that. That's just something that we can do if we're dealing with hardness or alkalinity. That's pretty common. Now, the initial pH was less than 8.3. So we know that there's none of that carbonate-based alkalinity. It's all bicarbonate alkalinity. That's something that we can see from the start. So we can basically say at or below, you know, if we have to add a bunch of acid, but we are below that pH 8.3, basically almost everything is in the bicarbonate, HCO3 minus. So they went ahead and said, okay, we'll just call that our C total, I think is what they're doing. So thus, bicarbonate equals 1.722 times 10 to the minus 3rd moles per liter, or 10 to the minus 2.76. We can compute the carbonic acid and CO3 2- from the given pH and the computed bicarbonate. Okay. We don't know anything about the ionic strengths. We're ignoring activity, and they do those calculations. So yeah, they're basically saying, well, at pH 7.2, and I'm going to flip back through a bunch of slides to find that graph. It's just going to be a little more convenient that way. At pH 7.2, we'll see it's almost all bicarbonate, right? We'd have to go below, I think that the next K value, pKa1, comes at 6.3 or something. So we could just take a look at the graph here. Yeah, sure, either one of those. And say, well, at pH 7.2, yeah, almost everything's bicarbonate. So we're good to call the C total whatever that was in terms of the bicarbonate alkalinity we calculated. So that's how they did it. They said, well, that's going to be C total, and there we go. Flip back forward. And of course, as we mentioned, you get the K values, you know the bicarbonate value, and you just use the two equilibrium equations that we know to calculate the H2CO3 minus, H2CO3 and the CO3 2-. Okay, and I think you guys can do all that. All right, so the last thing I want to talk about is just to really quickly come back to this graph we looked at when we talked about solubility. Now that we have all these tools in our belt to figure out what do our carbonate species look like in an open or closed system, we could go back through and really do a deep dive on how are each of these line segments calculated. And you'll notice all of those pieces that we just did could go straight into here, okay? Now, I want to give some time to chat about MATLAB or whatever else. I'm going to go real fast through this. Don't worry too much about it. The point here is that the solubility of this calcite depends on how much calcium is in there and how much carbonate is in there. So the diagram itself, we talked about these solubility diagrams. It's all hinging on that equilibrium with calcium and carbonate. We have an equilibrium constant, and so if carbonate changes, the amount of calcium that can exist may change. We may be able to have more or have less before we form a solid based on the carbonate changing. So the carbonate changing, which can change with pH, has a big impact on the solubility. Okay, so that's the point. And in a closed system, we can find three equations based on, and if you, surprise, surprise, these equations are showing up and changing right around our Ka values. So on the very far right over here, carbonate dominates. In the middle section, bicarbonate dominates. So we have an equation for that. And the last part, carbonic acid dominates. And we have a different function for that. Having some struggles over there, dropping things. Okay, so to derive equations for all of that and put it on a log plot, we can do very similar math derivations that we've been doing and then reference it with the equilibrium equation with calcite. Okay, so that's what's going on here. We take our equilibrium reactions. We first consider the scenario where we have the carbonate dominating. We can take, first of all, this is from our solubility, and we can then put that as a function, take the log of it, and essentially get that as a function of the carbonate concentration. And then we can take a look at the carbonate concentration at that range. It's going to be basically our C total in a closed system, so we figure that out. It's a nice little flat line. When we continue and do the next one, we're doing bicarbonate, the segment where bicarbonate dominates. The carbonate itself is dropping off as a function of pH. As we lower the pH, the carbonate's what matters, so we can see that the amount of calcium that can exist in the solution is increasing because the carbonate is decreasing during that range. Okay, and it's on a log plot, it's linear. That's the point, and we can see the pH dependence show up right here. and same derivation and equilibrium stuff that we've been talking about. Now, once we get below pH 6.35, then it's dropping off very strongly because we have a 2 times pH dependence. That H plus squared shows up, and when we take the log of that, that's 2 times pH. And so in that little segment, we are finally dropping off very quickly. There's practically 0 carbonate left when we're really much past pH 6.3, or that range. So we can plot it all that way, and at some point we get no calcite forming because there's no carbonate. Okay, so you can have infinite amount of calcium without forming the precipitation. So that all connects in with the solubility stuff that we've talked about. For the open system, again, it becomes fairly simple because the calculation for the CO3 minus becomes kind of a straight line. We do carry forward all of our pKa, so our K values, like we talked about earlier in the class, and this becomes the function, and that on a log-log plot, that becomes a straight line with a slope of 2 when we derive it as a log type of function. Okay, just wanted to connect those dots for you, kind of come back to that. Last thing I'm going to say is we didn't talk about hardness, but we certainly could and maybe should in this type of a class. Hardness is an important water quality parameter for aesthetic purposes. It's kind of how much, we did talk about it a little bit, how much magnesium and calcium essentially are there. We often express it alongside alkalinity. You know, it's related in indirectly, but it is related. And you know, we want to deal with it with precipitation reactions like calcite or similar ones, and the chemistry to do so is very much similar to this kind of stuff, where we add an acid or add a base, cause something to precipitate, add some extra carbonate to promote the precipitation. Then we strip that away and we manipulate the chemistry so that we precipitate solids and get rid of the minerals and go on about our way. So just wanted to mention that. Also might be fun if you visited different places to see, oh, how hard is the water over there? Okay, with that, I am open to questions, homework, MATLAB homework. Would you like me to tinker with MATLAB or? Okay, let me boot that up then. The first thing I'm going to say is what I would suggest you do. I would suggest you pretend for a moment that you're going to do it by hand. And what I mean by that is to never use chalk here. To set up a system where you will have x values, y1, y2. Now, in MATLAB, maybe the first thing to do would be to give yourself something very simple, right? Maybe we go 0, 4, 8, 12, and 14. So we have kind of the pH scale, just something like that, right? Whatever you like. Maybe fill that in. You could do this in Excel too. And then the first time, maybe just say, all right, y equals 2x. So maybe y equals 2x and y equals 4x, something like that. Just make yourself something silly, stupid that you can plot and double check and make sure everything is in fact working like you think it will. Okay? And so this is exactly what I was tinkering with today. And I'll go through that just to show you a good place to start to prove to yourself that you can make MATLAB make you a line and plot it. Okay? That would be the first step. Then you go and change the equation there. Okay? Based on the chemistry we talked about today. And I think I laid it out pretty clearly, so hopefully you could at least do it in Excel and say, okay, here's my alpha fraction. Here are all the pieces. Now Excel, go and do it, right? We could build a complicated equation in Excel. We could write it out. You could build a complicated equation and check what's your bicarbonate at pH 6, right? We almost did that a moment ago. So given some circumstance, you could fill in one or two of these. It might take a little while. It might be a little painful, like a homework problem or something. But you can do that, and maybe you should for one or two of them. So prove to yourself, I can do y equals the alpha fraction times CT. And then check to make sure that when you do it in code, it's going to work. Okay, so let me come over here, and we will, I'm just going to get rid of that. We're going to plot some lines here, okay? All right, so we want some x values. And I'm just going to go ahead and call it pH, right? pH values. And I want to set some range. And so I need to make some sort of a matrix, right? MATLAB is good with matrices. That's kind of what we do. So I'm going to put brackets. I'm going to say I want to start at 0, and I want to go to 14. That would be a simple way to do it. And if we did that, ran our code, and took a look at the output, we now have 15 columns, starting at 0 going up to 14. Okay? Now maybe I want a little better resolution than that. And maybe I want to give my computer a heart attack so I can tell it, well, give me a lot of very, very tiny steps, 0.000001. So I'm going to give my computer a heart attack and make it do that. Okay, and then I realized maybe I don't need that much accuracy. We're still only at 1.7. Maybe this is a waste of time. Okay, I'm going to do Control-C, which should stop it. And I say, okay, maybe just 0.1 is fine. Maybe 0.01, maybe 0.05, I don't know. How about 0.1? Boom, okay, there we go. Okay, so you can decide how fine you want to go there. And you saw it in live, trying to read out all of that, trying to compute all of that. It's basically we're taking it from 0 to 14 and stepping it, instead of the default by 1, we're stepping it by 0.1. Okay? That's just what I did. And you probably learned that in one of the intro things. I wonder if I could make this a little bigger for you. There we go. Okay, so now I don't really want to see that every single time I hit enter, so I'm going to put a semicolon there that kind of stops it from showing up. So again, that's each colon. If I just have one colon, then it's going to default to stepping by 1, but I can put a middle number there to say step by some other amount. Okay, so there's my x values. Got those now. Now I want a y1 vals, we'll say. And I don't know, what function do we want to do? We'll do x squared. What do we want to do? All right, so pH values, I think we can just square it. Okay, and I save that and I run it. Okay, I don't think squaring a matrix works so kindly. We can do this. We can square each one of the things in there. But if we just multiplied it, I think we can just multiply across the matrix. So we'll come back to squared. And this is testing my MATLAB stuff on the fly to make sure I can do it properly. I might not get the most efficient way. So let me first show you to confirm to ourselves that, well, if we just multiplied it by 2, we should get the same matrix and everything in it's multiplied by 2. So if you remember, matrix operations are a little different, right? That's what I'm struggling with the square. That was what went wrong. But let's go ahead and check with 2, and we can see that the last number is 28. That's very good, and we can scroll up to the top. The first one should be 0. The next one is 0.2. Another thing we could do is we could just check and say, let me call pH values the second cell in it, and that should be, that's giving me an answer of 0.1, which I thought was, oh, I'm sorry, Y values. Y1 vals should be, if we do check the second one in that, should be 0.2. Yeah. Okay, so it's working fine, as far as I can tell, except when I tried to square it. So if I want to square it, I think there's probably a better way to do this, but I'm going to do it the first way that comes to my mind, using a for loop. And I think there's probably a way to do this that just tells the matrix to do it more conveniently. But in case you need to do it this way, and for the sake of time, I'm going to say for, which tells MATLAB, we're going to do something several times. And then I'm going to tell you when to stop doing that thing. And so I'm going to say for some from I equals 1 to length of Y1 vals. So it's going to go for the total number of cells in the pH values that we made, or in the Y values we made. I should just do pH vals. They're the same length, these two matrix. And we can see that over on the right. They're 141 doubles. Double just means it's a matrix with numbers in it. But just to be clear with myself here, I'm going to say for that many times, for that many instances, I'm going to say Y1 vals. I'm just going to go ahead and get rid of this one because we don't need that. Y1 vals is going to be equal to, at I, is going to be equal to the pH values at I squared. And then I'm going to end that. So I think what this will do is go through for every, if I is like in Excel the number of rows, then for that many rows, I'm going to go through and check, well, what's in the first row? All right, 0. I'm going to take 0 squared is equal to this. Next one. And it does a for loop. It loops back and, oh, I should probably do this too. I equals I plus 1. I don't know if I have to. Maybe MATLAB changed that and I don't have to. But for every time we go through, it's going to bump I to the next one and do it over again. Okay? And yeah, I feel like maybe there's an update at some point and that's, they do that naturally now or something. But anyway, we're going to go to the next one and say, oh, okay, we're at 4. We're going to square that. Okay? So you can see this is one way to do it, to calculate every single value with your alpha fraction. Like I said, there might be a simpler way to do this that doesn't require for loops. If you ever get into coding hardcore, people will fuss at you for doing inefficient things. This is one of those things that's probably there's more efficient ways to do it. So pardon me, I'm not a pro coder. So let's see if this works. Okay, it computed something, so let's check. Oh. Y1 vals. Let's check the first one at 0. Should be 0, right? Oh, sorry. There is no 0th line, right? The first one is 0. Okay, good. Now 2 should be 0.1 squared, which would be 0.01 should be the answer, right? There we go. It is 0.01. So that's looking good. I think it worked. I'm curious. I want to see if it works if I comment that out. It looks like it works. So I don't. Oh, wait, maybe. Oh, sorry. Let me just check to see if it still has. Okay. Yeah, I think this is just silly. Don't need it anymore, so you can ignore that. That's kind of what's happening, though. It's doing that for loop. Okay, so we have some values, right? And we have squared those values. Now we need to plot them. And here's where I almost always go get some help from MATLAB. And even, it's already offering some help. Can't quite see it. Let me move this. And I think to myself, well, I know that MATLAB can plot things, but I forget the order. Do I put X first or Y first? So thankfully, it's giving me a little bit of a thing. And then maybe I want to do something else. Maybe I want to color it, or maybe I want to add a label. And then I want to make a second plot. What am I doing? So I do some mixture of help plot or help X label or whatever, try to find it, and go to Google or YouTube and maybe go to those tutorials that you went through and just get whatever help I need to figure out, okay, how am I doing this? So we're going to do Y values first, Y1 vals, comma. The X, actually, so now it's saying X1, Y1, so I'm going to change this. I'm going to say PH values, comma, Y1 vals. And then it says line spec, so I can add a marker style, a color, things like that. And I could put it cyan, and I think I could do little circles. I think that'll work. So let's try that, see what kind of plot shows up. Here we go. And if we zoom in a little bit, we can see they did become little circles because I put the O and I made them cyan. Now, maybe there's too much resolution for the circles to show up and maybe we don't really care about them being circles, but just showing you that you could do that. Okay? So the way I would start this is to double check that I can make 2 or 3 or 4 lines of some sort or functions across the pH values, not matching it to the chemistry yet, but just making sure I can do that in MATLAB. Then later come back and add in all the chemistry. Okay, so if you're not comfortable with MATLAB, start with something kind of simple. Look, if you delete all the spare lines, there's what, 4 or 5 lines of code to do that. So 10 including some miscellaneous stuff. So it's something that you can do. You've probably done it already with the assignments that you did along through the semester. So it's just a matter of getting in there saying, oh, can I do this? How do I do this? What am I doing? And making a plot. What I want from your submission is the .m file uploaded to Moodle. That's this little script that we're making here. And also take your plot and export it as a figure. So I'm going to do this one more time and show you. When you get your figure, you can go File, Save As, and save it as some .fig, or even like maybe a JPEG would be even better. So save it as your figure somewhere. That way I can run your code and also see the result and make sure that it's doing what it's supposed to be doing. Any questions before we get going? Yeah.
When you find the alpha 0 times the total concentration, do you find the log of that value and then graph it?
Yeah, so we're going to do a log graph. I don't remember if I specified that in the homework. I'll double check. But I want it to be log C versus log pH.
Okay, so once you do the alpha fraction times, this is just for the control point, you find the log of that.
Yeah, so you can find the concentration, take the log of it, and you're good to go. All right. Good? Okay. We'll see you on Thursday.